Alright guys, welcome to Polynomials, Linear Factors, and Zeros. What you really need to understand here is that using a zero of a polynomial can really help you factor the polynomial easier. So if you know a zero, factoring becomes a lot easier to handle. So that's the kind of what we want to think about throughout this this activity or this lecture. Okay, so in example 1, what is the factored form of x cubed minus 2x squared minus 15x? So we've done a lot of factoring with quadratics, but we really haven't talked about how to factor cubics or quartics, things of that nature. And so what you want to do here first is I rewrite the polynomial, and then I look and I think, well, factor out the greatest common factor. Each of these terms has an x term, so I'm going to start there. And so when I factor out an x, really it's dividing each of these terms by that x value, and in parentheses that's what's left. So I'm left with x squared minus 2x minus 15. So now I've got this quadratic inside parentheses. So what I need to do is to see if I can factor that, because they want to know the factored form of this cubic. So I got to see if what's left in parentheses is something that can be factored. So I'll factor the trinomial here. Two numbers that multiply to be negative 15 and add to be negative 2 are minus 5 and 3. Okay, so we have x minus 5, x plus 3, and that's what that factored form is. So here are our factors, the three factors of this trinomial. Now, we've talked about this before, especially with quadratics, but here are following things. So these are the following bullet points are all equivalent statements about real numbers b and the polynomial. Okay, quadratics are polynomials, so a lot of these you've already heard. Number 1, x minus b is a linear factor. Okay, that x is to the first power. B is also called a zero. It's also as a root or a solution. And b is also an x-intercept of your function. These are all equivalent statements, and you need to know those. For example, what are the zeros of x plus 2, x minus 1, and x minus 3? Graph the function. So all of a sudden I've given you zeros. Okay, so we have to look back at each of these three factors and figure out what makes each of them zero by the zero product property. So what would make x plus 2 0? X minus 2. What would make subtracting 1 0? Positive 1. 1 minus 1 is 0. And x minus 3, what makes that binomial 0? 3. 3 minus 3 is 0. So by the zero product property, x equals negative 2, x equals 1, and x equals 3 are the zeros of that polynomial function. Part 2 of this is to graph the function. So I know the zeros, so let's plot the zeros. X equals negative 2, x equals 1, and x equals 3. So 3, 1, and negative 2. Those are my zeros I plot first. Now we have to figure out how the function behaves in between the zeros. So let's find some points between the zeros. And notice I picked negative 1, 0, and 2. So between negative 2 and 1, we could use 0 and negative 1, which is what I've done. And then on the other side of 2, I've used, on the other side of 3, I could use 4, or I could use in between the zeros 1 and 3 is 2. So I could pick points outside to see where this function's behaving. But I didn't. I chose points in between the zeros. So we picked negative 1 and 0 because those are the two integers between the zeros. And then between 1 and 3, I've chosen positive 2. And I plugged them into the function. Okay, and I just did one example here. I plugged negative 1 back into the factored form on the previous slide. So I plugged in negative 1. So here's negative 1 plus 2, negative 1 minus 1, negative 1 minus 3. And I simplified here, and I got my answer. Now remember, we talked about end behavior. This is a cubic function. If I multiply this out, and the a value would be positive 1, so the end behavior is down up. Okay, that's how the down up, that's how our polynomial is going to behave. So once I plot the zeros, I find the points between the zeros, and then I go ahead and plot those. So that's what I've done here, here, and here. 0, 6, negative 1, 8, and 2, negative 4, and then I connect the points with a smooth curve. I know that I have my 2 turning points, and we'll talk about turning points later, and my graph's going to go down, up. Okay, I can see that it continues going down. I can put negative 3, negative 4 into this function and see that the graph's going to continue in a negative direction. Same thing with values after 3. Now, the factor theorem. What the factor theorem tells us is the expression x minus a is a factor of a polynomial if the value of a is a 0 of the related expression. Meaning, if I plug in a number, I get 0. So if I looked here, if I wanted to plug 2 in here, I got 2 minus 2, that would be 0. And that's what the factor theorem is telling. Okay, if this is a factor, if I plug a into that factor, I should get 0. That's what the factor theorem is talking about there. So, for example, what is the cubic polynomial in standard form with zeros, negative 2, 2, and 3? So what they're talking about here is the relationship between factors and zeros. So I have my zeros. So I have to build my factors so that when I plug in each of these numbers, I would actually get 0. So notice, I start with x minus 2 here. If I plug 2 minus 2, I get 0. If I go to the next one, negative 2 plus 2, I get 0. And finally, 3 minus 3, I would get 0. So that's what they mean using the factor theorem here. Okay, I have to build my factor or my factors from my zeros so that if I plug my zeros into these factors, I better get 0. Now, I want you to be careful here because I could plug 3 in here. 3 minus 2 works. 3 plus 2, I don't get 0. However, the last one I'd get 0, which makes this whole thing 0. So I don't want you to think that when you plug in these zeros, each one of these binomials has to be 0 when you plug in that 1x. It doesn't. Only one of them has to make a 0 because when you multiply a number by 0, you get 0. So if you notice here in red, that's the difference of two squares pattern. So they want to know what is the cubic polynomial in standard form. This is factored form, so I have to multiply those binomials out. It just so happens is we have that difference as two squares pattern here. Okay, they're conjugates, so I get x squared minus 4. And then I just have to multiply that to x minus 3 using the distributive property. Some of you might say FOIL. You can use box method here. And I get x cubed minus 3x squared minus 4x plus 12. That is the polynomial in standard form. Largest power to smallest power. And it's also tying in the factor theorem. Multiplicity, this is a great, I really like talking about multiplicity, and it's really easy to see from graphs. And so we're going to spend some time in class, and I'm going to make some other videos with the graphing calculator to show you what they mean by multiplicity. Basically, multiplicity is just how many times a factor repeats. And however many times a factor repeats, that the 0 is going to behave like how many times that factor repeats. For example, if I have a factor that repeats twice, so if I come down here and say, well, let's have x minus 3 squared times x plus 4. Let's just say that's my polynomial. This would be a multiplicity of 2 because the factor repeats. So the 0 here would be 3. Okay, so what the multiplicity tells you is that I look for the multiplicity. I see that's a power of 2. So the multiplicity of the factor x minus 3 is 2. So the 0, x equals 3, has a multiplicity of 2. So it's going to behave like a quadratic function there. So at the 0, 3, you're going to notice the function is going to behave like a quadratic. It's going to have a general shape of a quadratic there. We'll look and we'll see some examples from another video under supplementary material, and you guys can look at that example, and I'll plot some of these. So multiplicity, how many times a factor and a 0 repeat? However many times that factor 0 repeats, it's going to behave like that function at that 0. So if it's 1, you would behave linearly. If the multiplicity is 2, like here, you would behave like a quadratic, and if it's a multiplicity of 3, you'd behave like a cubic, and so on. So if you have a multiplicity of 4, it'd behave like a quartic. Again, we will see examples of this not only in class, but on a supplementary video I'll make using the TI emulator, so you can visually see this better. Okay, so in this last example, what are the zeros of this function, f of x equals x to the fourth minus 2x cubed minus 8x squared? What are the multiplicities? How does f of x behave at these zeros? Okay, so I have my function. I really want to know the zeros so I can determine the multiplicity. I go ahead and factor out an x squared, the GCF, because x squared is the largest term that goes into all three terms. So I factor out the x squared and I'm left with x squared minus 2x minus 8. Like the first slide, can we factor what's in parentheses first? And now. So we can, x plus 2 and x minus 4. These are linear. Okay? The zeros here are negative 2 and positive 4. They both have a multiplicity of 1 because the factors don't repeat. They're not raised to any power other than 1. So the 0, negative 2, behaves linearly and has a multiplicity of 1. 4 is another 0. That has a multiplicity of 1 and will also behave linearly. However, x squared, you see x, okay, being squared, that's the same as x minus 0 squared, isn't it? So x equals 0 is the 0 of x minus 0. So that's going to behave like a quadratic function there because the multiplicity is 2. And so x equals 0 will behave like a quadratic at 0. And I'll graph this one specifically for you on the TI-84 emulator under supplementary material for you guys to look at. Okay? If you guys have any questions or comments about anything you've seen in this video, you can go ahead and email me at nicholas.bennett@dc.gov, or you can just type in your questions or comments below. We'll see you next time.